This continues the astronomy lectures within the context of Newtonian gravitation. One of the most important parameters that you can know about a star is its mass, because ultimately the mass of the star determines everything else about the star. It determines, for example, its size, it determines its color, it determines its temperature, and it also determines how long the star will live. For example, let's say that you have a star that has a relatively low mass. What this then means is that the rate of nuclear fusion that occurs in the core of that star is slow. So then therefore that star will not burn through its nuclear fuel all that quickly, and it will last a long time. If, however, a star is very massive, then the core of that star is extremely hot, and then therefore the rate of nuclear fusion that takes place in its core is extremely high. This then means that very rapidly a star such as that will burn through all of its nuclear fuel, and then therefore its lifetime will not be very long. Basically, the rate of nuclear fusion that occurs in the core of a star determines basically everything else about the star. Determines its color, its temperature at the surface. It also determines how long it will live. In the case of the sun, for example, will last for about roughly 10 billion years or so. Right now, the sun is more or less about halfway through its lifetime. So how do you measure the mass of a star? The easiest way to measure the mass of a star is just watch what happens, for example, when two stars are in orbit about each other. A single star system, such as that of the solar system, is actually somewhat in the minority in terms of the populations of stars in a typical galaxy. Only about 30% or so of the stars in the typical galaxy are single star systems, such as our solar system. Most star systems, when we observe them in the galaxy, most of those systems consist of at least two or more stars. In the case of our nearest stellar neighbor, Alpha Centauri is actually a triple star system. You have two stars that are in orbit about each other like so, about what is called their common center of mass. And then much further out is a third star that's in orbit around the other two. It just so happens that that third star happens to be closest to us at the moment. It's at a distance of about 4.2 light years, whereas the two other stars in orbit around each other are at a distance of about 4.3 light years. The star that is closest to us in this triple star system is called Proxima Centauri for this reason. If you observe two stars, for example, in orbit about each other, you can then do a quick calculation to determine their mass. The easiest situation for us to take a look at is a binary star system that consists of two stars of equal mass. Because each star exerts a gravitational force on the other, the two stars will orbit each other. They will orbit about their common center of mass, which is a topic that we'll look at a little bit later on in the semester. As long as the two stars have an equal mass, then therefore their common center of mass will be exactly halfway in between them. This is, by the way, a detail that we have been ignoring throughout these descriptions of gravitation thus far. In our descriptions of gravitation thus far, for example, say when a planet orbits the sun, we've thought of the sun as stationary in the center of the diagram, and the planet just orbits around it, for example, in uniform circular motion. That's not quite the case, however. The planet also exerts a gravitational force on the sun. So then therefore the two objects, the sun and the planet, they orbit about their common center of mass like so. So think of it this way. It's like the gravity associated with Jupiter causes the sun to wobble a little bit as Jupiter orbits the sun. So as all of the planets orbit the sun, ultimately all of the objects are orbiting around their common center of mass. This is something that we've been ignoring in the topics thus far. Okay, now with respect to this binary star system consisting of two stars of equal mass, we've turned it here into a problem. Go ahead and copy the problem down into your notes. Let me read you the details here. We have two stars of equal mass. They orbit their common center of mass, which is exactly halfway in between them. The two stars are 10 AU apart, and they complete an orbit once every 8 years. Using those two numbers, we can then ultimately calculate how massive each star is in terms of solar masses. So here's our basic setup for this problem. It is definitely a little bit different than the examples that we've looked at thus far. Okay, so right here, for example, is the circular orbit associated with these two stars. Okay, here's one star of mass m. Here's the other star also of mass m. And then right here is their common center of mass, which is exactly halfway in between them. Basically, the two stars do this, like so, always being directly across each other as they orbit around their center of mass. Okay, now the diameter of this circle is given as the distance here as 10 AU. So that diameter is twice the radius. That's 10 AU, therefore the radius of the circle is 5 AU. Okay, and then the two stars complete an orbit once every 8 years. So the period is 8 years. Let's immediately go ahead and convert these numbers into the units that we need, the distance in terms of meters, and the time here in terms of seconds. So let's go ahead and multiply by 1.5 times 10 to the 11th meters per AU. AU cancels out. So this then ends up being a total distance here of 7.5 times 10 to the 11th meters. And then the amount of time here, I'm going to go ahead and convert this into seconds. So multiply by 3.15 times 10 to the 7th seconds per year. Okay, years cancels out. So 8 times that. And this ends up being then 2.52 times 10 to the 8th seconds, like so. So now everything is in the correct units. Here's then how we set up this problem. Let's go ahead and take a look at the force of gravity that's exerted upon this star due to the other one. This then causes a centripetal acceleration inwards towards the center of the circle. And now here's how we write F equals ma. Remember that the force of gravity doesn't depend upon the radius of the circle. It depends upon the distance between the two objects, which in this case is the diameter of the circle. Therefore, we write F equals ma in the following manner. We have the force of gravity exerted on that star due to the other one, divided by the distance squared, rather. Here is the force itself. And this then equals mass times acceleration. The acceleration is a centripetal acceleration, where once again the centripetal acceleration depends upon the radius of the circle. Okay, now let's go ahead and simplify here. We can go ahead and cancel out the mass of the star like so, but this one remains, and now this then is what we're going to solve for. Okay, let me go ahead and square the denominator of the expression. I'll move to the lower board, remove this information from the previous lecture. Okay, now here on the left-hand side, I'm going to go ahead and square the denominator. That then gives me this, like so. At this point, we can go ahead and cancel out one of the r's here and here, but notice that this 4 remains. Okay, now we're going to make the following substitution for the speed v. It's the circumference of the circle divided by the period. So over here on the left, I have gm over 4r equals then v squared on the right-hand side. I go ahead and I plug in my terms, square each one, and when I do, I obtain this. So once again, what we're seeing here is Kepler's third law. It's now just in a different mathematical form than the examples that we've seen thus far. And then what we have to do is we have to solve for the mass m. All right, so to solve for the mass m, I'm going to first of all have here 4 times 4, which is 16 pi squared, and then r cubed, and then divided by gt squared. Notice once again that this problem is a little bit different than the other examples that we've looked at thus far. Okay, let me go ahead and plug in here. So 16 times pi squared, and then multiply by r cubed. All right, so up on the top board, we have 7.5 times 10 to the 11th, and then we cube that, and then divide by gt squared. So I'm plugging in capital G into my calculator, and then multiply by, there we go, 2.52 times 10 to the 8th squared, quantity, equals about 1.6 or so times 10 to the 31 kilograms. Now we'll compare this to the mass of the sun. We'll divide by 2 times 10 to the 30th kilograms. So if I divide by 2 times 10 to the 30th kilograms, this then gives us about 8 solar masses or so. So these two stars are rather massive, like so. At 8 solar masses, each of these stars would not last as long as the sun. So this is one basic way in which astrophysicists can measure the masses of various stars. Just watch what happens, for example, as the two stars, in this case, orbit about each other. Lastly, for this problem, you may be familiar with a binary star system from some common fiction. For example, the planet Tatooine in Star Wars, if you recall episode 4, A New Hope, when Luke Skywalker walks outside to watch the sunset. When he watches the sunset, you see two stars that are very close to each other. So in that particular star system, this is what's referred to as a tight binary. The two stars are in orbit around their center of mass like so, and then the planet Tatooine orbits the two stars much further out like that. When we do look out into the universe, we do in fact see star systems that are just like Tatooine in Star Wars. And keep in mind that Tatooine in Star Wars was written 40 years ago.